Morning, everyone. Are you able to see my slides? Good morning. Are you able to see my slides? Okay, great. So let me scroll down to the relevant portion.
Seems to be fine.
Well, are you able to see page number 81? Page number 81 is visible? All right. Okay, so page number 81 is not visible.
There may be a little lag. You want me to exit all these other things?
Oh, I see. It's still showing the first page.
Instead of page number, ask about the content on the page.
They are seeing the first page. It's still the introduction slide. Okay,
Okay, thank you very much.
let me try.
ठीक है हो रहा है मतलब ब्लैक के बाद अब तक तो आ जाना चाहिए लास्ट में
कौन सा फाइल पे क्लिक करने से तुम जा रहे हो? Now are you able to see page number 81? Okay, I think now we are able to go from one slide to another, that we that indeed, if you take a state alpha beta column vector representing the spin degrees of freedom of a spin half particle like electron or a proton or a neutron, then under a rotation of the coordinate system by Are you able to see now? Are you able to hear me? All right. So, and had just started last time about the relation between the SO3 group and the SU2 group. Let us recall that the 3x3 matrix representation of the SO3 group leaves the distance from the origin to a point invariant. That means r square, which is equal to x square plus y square plus z square, that is invariant under rotation, which is generated by the SO3 group. So the question here is, does SU2 also lead to some kind of a rotation of the coordinate system and also leave r square invariant? To see this, what we do is to take a look at any complex valued 2 cross 2 Hermitian matrix that is traceless. So any complex 2 cross 2 Hermitian matrix that is traceless must have the form of this matrix capital X, where all the entries Z, X, Y, they are real numbers. And as you can see, this is the most general 2 cross 2 matrix. It is traceless because if you sum up the diagonal elements, it is 0. It is Hermitian because Z diagonal entries are real, while off diagonal entries are complex conjugate of each other. But then we also realize that because the polyspin matrices are of the form that sigma z is 1 minus 1 in the diagonal, off diagonal is 0, sigma x is 0, 1, 1, 0, and sigma y is minus iota 0 in the diagonal, off diagonal entry minus iota and iota. So therefore, any complex 2 by 2 matrix which is Hermitian and which is traceless can be written as x into sigma x plus y into sigma y plus z into sigma z. Also, let us look at the determinant of this matrix capital X. If you look at the determinant, then the determinant of X will be multiply the diagonal elements, which is minus z square, minus x minus iota y into x plus iota y, which is nothing but minus z square minus x square minus y square. In other words, determinant of x is simply minus of r square. So equation 71a and 71b tells us that a matrix capital X which has the elements z x minus iota y in the first row and x plus iota y minus z in the second row, its determinant is simply negative of x square plus y square plus z square. Okay. So therefore, we can ask what happens to this matrix capital X if we consider a similarity transformation generated by any element A belonging to the SU2 group. All right. So suppose A is an element of SU2 group. And since SU2 group is a group containing unitary matrices whose determinant is 1, then A inverse is A dagger itself, and therefore the similarity transformation brought about by an element of SU2 of X is X gets transformed to X prime equal to A multiplied to X multiplied to A dagger, because A dagger is A inverse as A is a unitary matrix. Now I will prove a particular result, and the statement of the result is this. If X prime is equal to A dagger, that means X prime is related to X by a similarity transformation generated by an element of the SU2 matrix A, then X prime is also traceless, X prime is also Hermitian, and the determinant of X and X prime are identical. Okay? So let's prove that. First, let me prove that X prime is Hermitian. Since X prime by definition is AX A dagger, the Hermitian conjugate of X prime, that is X prime dagger, will be Hermitian conjugate of AX A dagger. But we already have learned from our linear vector space and linear operator course that dagger of AX A dagger will be A dagger dagger, X dagger, and A dagger. And similarly, we have also shown in our linear vector space course that A dagger dagger is simply A itself. And therefore, what we find is that X prime dagger is A X A dagger, but AX dagger is simply X prime. So equation 72A proves that X prime dagger is X prime. In other words, X prime is a Hermitian matrix. Now let's consider the trace of X prime. Trace of X prime is nothing but summing of the diagonal elements. So the diagonal elements of X prime are the II component of X prime. In this case, of course, is the case where I goes from 1 to 2. So trace of X prime is summation I going from 1 to 2, X prime II. But X prime II is nothing but II component of AX A dagger. And since AX A dagger is the product of the matrices AX A dagger, we also have to consider the II element of the product. And II element of the product is nothing but first you take matrix A and multiply matrix X, and the IK component of AX is simply AIJ XJK summed over J, and then this IK element of the matrix AX is multiplied to KI element of matrix A dagger, and then sum it over K. So now we have three sums. The sum over I from 1 to 2 was because we were taking the trace. The sum over J and K come about because we are multiplying the matrix A with X and then multiplying AX with A dagger. But since A dagger Ki is a number now, because the Ki element of the matrix A dagger, therefore I can place it on the leftmost position so that this equation becomes sum over I, J as well as K, the Ki element of A dagger multiplied by Ij element of A multiplied by Jk element of X. But A dagger Ki multiplied by Aij sum over I is nothing but the Kj element of the matrix A dagger A by virtue of the multiplication rule of matrices. So A dagger Ki multiplied by Aij summed over I is the Kj element of A dagger A. But A dagger A is identity because A is a unitary matrix, and therefore Kj element of A dagger A is Kj element of identity matrix, but that is nothing but the Kronecker delta Kj element. So after summing over I, we find A dagger Ki Aij is simply Kronecker delta Kj. Now if I sum over K of delta Kj multiplied by Xjk, when I sum over K, only that term will be non-zero when K is equal to J, because Kronecker delta by definition is 1 when K is equal to J, 0 otherwise. So when K is being summed over, delta kj xjk will be non-zero only when k is equal to j, and when k is equal to j, delta jj is 1 and xjk will become xjj, and therefore we have the sum. I have summed over j first, so I have the sum over k going from 1 to 2, xkk. That is, I have summed over j, and only when j is equal to k, the contribution will be non-zero, and we get the result that indeed the trace of x prime is equal to sum over k xkk, which is nothing but trace of the matrix X. So in other words, we have shown the trace of X prime matrix is same as the trace of X matrix. Now let's look at the determinant. So determinant of X prime by definition is determinant of AX multiplied by A dagger. But you all know that if you take any finite dimensional matrices P and Q, determinant of P into Q is determinant of Q into P. And because we are talking about 2 by 2 matrices, this result will hold in this case too. And therefore, determinant of AX into A dagger is same as determinant of A dagger into A X. But A dagger A is simply identity element, and identity into X is X, and therefore determinant of AX A dagger is simply determinant of X. So therefore, we have shown X prime is Hermitian if X is Hermitian, X prime is traceless if X is traceless, and we have proved that determinant of X prime is determinant of X, thereby proving the corollary. Okay. Now, if X prime is also traceless and Hermitian, X prime can be also written in terms of polymatrices. So indeed, X prime will be therefore some X prime into sigma X plus Y prime into sigma X plus Z prime into sigma Z, because we have already argued that any Hermitian and traceless matrix can be written as a real number multiplied by sigma x plus another real number multiplied by sigma y plus another real number multiplied by sigma z. I can see that there is a typographical error in equation 72c. The second term on the right must be sigma y. So the right equation is x prime sigma x plus y prime sigma y plus z prime sigma z. And the determinant of x prime, just like determinant of x was minus x square minus y square minus z square, because x, capital X, was x sigma x plus y sigma y plus z sigma z. In this case, determinant of x prime will be minus x prime square minus y prime square minus z prime square. But we have proved in equation 72c that determinant of x prime is also determinant of x, and determinant of x was minus x square minus y square minus z square. In other words, what we have proved is that not only the matrix capital X prime is x prime sigma x plus y prime sigma y plus z prime sigma z, we have also proved that determinant of x prime is same as determinant of x is same as minus r square. So in other words, the similarity transformation ax a dagger, which gives us x prime, generates a transformation of the coordinates x, y, z going to x prime, y prime, z prime, such that x prime square plus y prime square plus z prime square is equal to x square plus y square plus z square. In other words, the similarity transformation Ax A dagger is nothing but a result of SO3 rotation, because SO3 rotation precisely does it. It transforms x, y, z coordinates to x prime, y prime, z prime coordinates such a way that x prime plus y prime, x prime square plus y prime square plus z prime square is x square plus y square plus z square. Okay, and hence x prime equal to ax a dagger similarity transformation connects the SU2 group with SO3 group. So let us summarize. SO3 group element transforms x, y, z to x prime, y prime, z prime in a way that the x prime square plus y prime square plus z prime square is equal to x square plus y square plus z square. Analogously, if you take a matrix capital X, which is characterized by the coordinates x, y, z, and capital X is simply z, x minus iy, x plus iy minus z, when you perform a similarity transformation of such a Hermitian traceless matrix by an element of SU2 group so that x goes to x prime equal to ax a dagger, then x prime is characterized by three other real numbers x prime, y prime, z prime, and under this similarity transformation x prime square plus y prime square plus z prime square is equal to x square plus y square plus z square. In other words, the similarity transformation due to an SU2 group element causes a rotation of the coordinates x, y, z to x prime, y prime, z prime. So indeed, SU2 group element under a similarity transformation also causes a rotation in which a traceless Hermitian matrix X characterized by the three real numbers x, y, z is rotated and it goes to another traceless Hermitian matrix capital X prime given by ax a dagger. Now you can ask, does it mean that for every SU2 element and every SO3 element there is a one-to-one mapping, or in other words, is there an isomorphism between the SU2 group and SO3 group? The answer is no. Of course, there is a homomorphism between the SU2 group and SO3 group. That means every element of SU2 group can be mapped to an element of SO3 group, just like what we showed for every element of A belonging to SU2, there is a rotation matrix belonging to SO3 that we have already shown. However, note that because the similarity transformation x prime equal to ax a dagger, the same similarity transformation is there also if instead of a we had used the element minus a. Okay, why? Let us go through it systematically. Note that both a as well as minus a lead to identical similarity transformation of x to x prime, because A will give us x prime equal to A x A dagger, and what will minus A give us? Minus A will transform x to minus A into x into minus A dagger, but minus A x into minus A dagger, minus into minus will be plus, is same as A x A dagger. In other words, this point B shows two SU2 group element A and minus A lead to the same SO3 transformation of XYZ. And how does one, what is the relation between A and minus A? If you go back to our form of the group element A in terms of the three parameters zeta, chi, and psi. So let's go back when we discussed a general element of the SU2 element. Right. Look at equation 67E. A general element of the SU2 group was given in terms of three real parameters, zeta, chi, and psi. Okay. And therefore, the first row was e raised to power I chi cos zeta. Second element of A was e raised to power I psi sin zeta. First element of the second row was minus e raised to minus I psi sin zeta. And the last element was e raised to power minus I chi cos zeta. Note that if I now substitute instead of chi, chi plus pi, psi as psi plus pi, then you see e raised to power I of chi plus pi is nothing but minus e raised to power minus e raised to power I chi cos zeta, because e raised to power I pi is minus 1. Similarly, e raised to power I psi plus pi is e raised to power I pi multiplied by e raised to power I psi, but e raised to power I pi is minus 1. So this also element becomes negative of itself. And similarly, these also change sign. And hence, the A and minus A element of SU2 are related to the parameters. So if chi and psi represented the matrix A, then substituting chi plus pi, and for psi substituting psi plus pi, the SU2 element that you get is minus A. And both A as well as minus A generate the same similarity transformation AX A dagger, and therefore for every SO3 group element there are two SU2 group elements, and hence there cannot be any isomorphism. There is a homomorphism, but there cannot be any isomorphism. Okay. We also have noted earlier that SU2 group plays a very important role in describing the spin angular momentum, which are the intrinsic angular momentum for spin half particle. In particular, the generators sigma x by 2, sigma y by 2, and sigma z by 2, the generators of SU2, they have the same Lie algebra as the Lie algebra of the SO3 group, as well as the Lie algebra of the angular momentum operators in quantum mechanics. And that is precisely the reason why h bar into the sigma x by 2, h bar into sigma y by 2, and h bar into sigma z by 2. They are the spin angular momentum operators for the spin half particles. And we also have seen that just like SO3 group element, when it operates on XYZ, they rotate the XYZ coordinates. Similarly, the 2 cross 1 spin doublet alpha beta describing the state, quantum state of the spin degrees of freedom of spin half particle, they also rotate under the application of SU2. However, applying SU2 about any axis rotating by 360 degree doesn't bring back the spin state to itself, but there's a negative sign, overall negative sign that comes about. If you want to get back the spin state, you have to rotate by 720 degrees. But SU2 also plays a very important role in nuclear physics and particle physics. In particular, the, as you know, neutron and protons, although they have different electric charge, but as far as strong interaction is concerned, they behave approximately in an identical fashion, and therefore the neutron and proton are described by isospin quantum numbers. So the isospin degree of freedom is also described by the SU2 group. And furthermore, in fundamental high energy physics, as shown by Salam, Weinberg, and Glashow way back in 1964, 1965, that if you wish to unify the weak interactions that are responsible for beta decays in nuclear physics, if you want to unify the weak interaction with the electromagnetic interactions, then the left-handed components of leptons like neutrino electrons, muon neutrinos, muons, and tau lepton neutrino, tauons, tau lepton, these left-handed doublets, they transform under SU2 group element. And similarly, the left-handed quark doublets like U and D quark, charm and strange quark, top and bottom quark, okay, they also, the left-handed components transform under SU2 group. And of course, both the electromagnetic interaction, we know they transform under the U1 group. We have already studied U1 group before. And the electromagnetic interaction transform under space-time dependent U1 group, the so-called gauge symmetry of the Maxwell's equation. Here also, the SU2 group, it is a space-time dependent SU2 group, which is the symmetry for the left-handed doublets, both for the leptonic sector as well as the quark sector. And therefore, SU2 indeed plays a very important role in the electroweak unification, as was shown by Salam, Weinberg, and Glashow in the mid 1960s, and they were given the Nobel Prize in 1979 after one of their predictions concerning neutral current was shown to be correct in accelerator physics results. Now we will very briefly discuss the SU3 group, because SU3 group also plays a very fundamental role in strong interaction. SU3 group are again the group consisting of 3 by 3 complex valued matrices which are unitary, as well as their determinant is plus 1. That's why SU3, that means special unitary group having 3 in the 3 uh, dimension. So 3 cross 3 matrices are their fundamental representation for SU3. And because the special unitarity gives us 3 square minus 1 uh, independent degree of freedom, so we find that the number of real parameters that describe an element of the SU3 group is 3 square minus 1, which is 9 minus 1 is equal to 8. So the SU3 group element is characterized by 8 independent real parameters, just like SU2 group, SU2 2, so 2 square minus 1 was 3. SU2 group was characterized by 2 square minus 1, which is 4 minus 1, 3 real parameters. SU3 group is characterized by 8 real parameters. And also related to this 8 real parameters, because it's also a gauge theory, that means space-time dependent SU3 group is a symmetry of the quantum chromodynamics, and number of generators will be also equal to 8, and therefore the number of independent gauge field describing the strong interaction will be also 8. So there'll be 8 types of gluons for the quantum chromodynamics, because there are 8 generators in this case. Now, one can identify the generators by again recoursing to infinitesimal elements of SU3. But since these are 3 by 3 matrices, the algebra is going to be more messy, but it can be done. What I will do in this brief discussion is directly give you the result, just like we had done in the case of SU2 by using infinitesimal SU2 elements. We had identified the 3 generators sigma x by 2, sigma y by 2, sigma z by 2. Analogously, you can use similar technique to identify 8 generators of SU3, and the 8 generators are lambda 1, which is 0, 1, 0, 1, 0, 0, 0, 0, 0. As you can see, the first block diagonal is related to the polymetric sigma x. You can see the first 2 cross 2 block diagonal element is related to sigma x. The second generator is sigma 2, which is 0 minus I 0, I 0, 0, 0, 0, 0. Again, you can see that the top block diagonal element 0 minus iota I 0 is nothing but sigma y of the poly spin matrices. Lambda 3 generator is 1, 0, 0, 0 minus 1, 0, 0, 0, 0. Again, you can see the first block diagonal part 1, 0, 0 minus 1 is nothing but the sigma z poly spin matrix. Again, you can find that lambda 4, lambda 5, lambda 6, and lambda 7, they are related to polyspin matrices. You can easily check the elements. However, lambda 8 in this representation has a different form, Lambda 8 is completely diagonal, and the diagonal elements are 1 over root 3, 1 over root 3, and minus 2 over root 3. Okay. The Lie algebra of SU3 from these 8 generators that I have put down, you can directly multiply the matrices, take the commutation of the commutator bracket of the matrices, and you can prove that the Lie algebra of SU3 given by the commutator bracket of lambda j, lambda k, where j, k, m are all going from 1, 2, 3 up to 8 because there are 8 generators. The Lie algebra commutator bracket of lambda j, lambda k is 2 iota f j k m lambda m. Again, m and m are repeating so that they are being summed over. But here, the structure constants fjkm, of course, is totally antisymmetric, but the numbers for different components of fjkm are somewhat more complex. And here I have given you the all the non-zero values of the structure constants. So F123 is 2. And because FJK is totally antisymmetric, you know if F123 is 2, then F213 is minus 2. And similarly, F321 is minus 2, and so on. Here I have put down only the non-zero components of the FJKM, and the non-zero structure constants are F123 is 2, F156 is minus 1, so is F367, while 4 of the structure constants, F147, F246, F257, F345, are all 1, while F458 and F678 is root 3. So, of course, SU3 group is somewhat more involved than the SU2 group, just like SU2 group was more involved than the U1 group. U1 group was the simplest Lie group, which was an abelian group. SU2 is a non-abelian Lie group, and SU3 is also a non-abelian Lie group because the generators of SU3 group, as we saw, do not commute. Right, as I have already mentioned that quantum chromodynamics, or in short QCD, is a gauge theory that describes strong interaction seen in particles. Strong interaction is what keeps two protons in a nucleus bound to each other. Note that protons being having positive electric charges, two protons, they repel each other by means of electrostatic forces. However, in a nucleus that has more than one proton, like helium nucleus or carbon nucleus and so on, what keeps all the protons together? After all, they have repulsive electrostatic forces. What keeps them together is much stronger force which keep neutrons and protons bound to each other in the nuclei of atoms. And these strong interactions, their fundamental theory is given by the theory of quantum chromodynamics. And in quantum chromodynamics, the fundamental constituents of protons, neutrons, and any other hadrons are the quarks U, D, then S quarks. UD correspond to up quark, down quark. S quark corresponds to strange quark. C quark correspond to charm quark. T quark corresponds to top quark, and B quark corresponds to bottom quark. So UDSCPB, all these quarks are the fundamental constituents, and each of the quarks, they carry three distinct quantum numbers associated with the SU3 group. In other words, any quark, whether it U, D, or S, any quark Q can be represented as Q1, Q2, Q3, 3 cross 1 column vector, and SU3 group element will act on the column vector Q1, Q2, Q3 and make it Q1 prime, Q2 prime, Q3 prime. They'll mix up Q1, Q2, Q3 and make it Q1 prime, Q2 prime, Q3 prime. And these degrees of freedom of this fundamental representation, Q1, Q2, Q3, are essentially called the red, blue, and green degrees of freedom. And just a historical thing, just like in colors, you have three primary colors, red, blue, and green. And when you combine red, blue, and green equally, you get a colorless object like white. Similarly, when Gell-Mann used the SU3 group to talk about quantum chromodynamics, he called the SU3 degrees of freedom, the three distinct quantum numbers, as colors, because when a quark has the same equal proportion of the three quantum numbers, then the quark doesn't interact strongly. So that's why he gave them the name red, blue, and green. Although the SU3 group doesn't have anything to do with the colors, it's just a name for the three quantum numbers associated with the SU3 group element. And it's a gauge theory. That means space-time dependent SU3 element mixes up the color components of a quark state. Because it's a gauge theory, that means space-time dependent group element works, there are gauge fields associated. These are the gauge bosons of the QCD called the gluons, which mediate the strong force between quarks. And because there are 8 generators, there are 8 distinct gluons which mediate the strong forces between the different quarks. And at the fundamental level, therefore, it is the SU3 group which plays an important role in describing the strong interactions of high energy physics. Okay. Right. So now what I will do is that I will start, because we are having very less number of lectures. I will also have to take an extra class in lieu of the yesterday's class that could not be held because of the internet problem. I will take an extra class on Tuesday evening. But in the remaining time, let me start our last topic of mathematical physics, okay? And that is the notion of the complex numbers and complex variables. At the moment, I will say in words, we all know how mathematicians, they introduced the field of complex numbers. We know that a quadratic equation like x squared plus 1 equal to 0 has no real solution. Real numbers, they were a generalization of fractions. As you know, integers and fractions, they corresponded to counting. In day-to-day life, when we count, then it is the natural numbers which come to us. And similarly, when we subtract natural numbers from one another, we get the concept of negative numbers. And when we divide a group of numbers like group of oranges or group of apples, you get fractional numbers. And then mathematicians realized that fractions cannot be all, there has to be irrational numbers, and the whole field of real numbers, which are the union of irrational numbers and rational numbers like rational fractions, came about. And the real numbers were very representative of quantities that we see in our physical world. So, whenever we make any measurement, whether we measure length or whether we measure time, whether we measure mass, we measure current, we measure uh, angular momentum in classical physics, linear momentum, the result of all measurements were in terms of real numbers. However, when mathematicians were talking about solutions of quadratic equation, cubic equation, they found that certain equations have no real solutions. Like x squared plus 1 doesn't have a real solution. And therefore, they suggested that why not generalize? Let's say we write x square equal to minus 1 for x square plus 1 equal to 0, and we will say that plus minus square root of minus 1 is a solution to x squared plus 1 equal to 0. It is true that it is quite an imaginary solution, plus minus square root of minus 1. Nevertheless, we can develop an abstract field of mathematics by including such concept as plus minus square root of minus 1 as our generalization of numbers, and therefore a whole field of complex variable and complex analysis started, namely writing down numbers in terms of two real numbers. So they mathematicians said let z be a complex number equal to x plus iota y, where y iota is defined to be square root of minus 1. And soon, mathematicians found that one can play around with this complex numbers x plus iy. You can multiply x plus iy to x plus x prime plus iy prime. You get other complex numbers. You can add them. X plus iy plus x prime plus iy prime is simply x plus x prime plus iota into y plus y prime, and so on. And they found there develops an abstract but beautiful structure, and that formed the subject of complex analysis. So on Tuesday in the evening at 8 p.m., we will have our next class where we will talk more about complex analysis. Now, if you have any question, you can ask me. Okay, you can type in the box. Okay, you can type in the box. Yeah, I can see already a question by Sahil. Yeah, so when we talk about generators, there's a generator for the SU2 group. Lagrangian doesn't figure in. Lagrangian is in physics. We are talking about mathematics. Okay. So generator, when we talk about generator of a Lie group, we are talking about the Hermitian matrix by which I can generate a Lie group element. Okay, Lagrangian is nowhere in the Picture. Lagrangian is in physics. Lagrangian doesn't enter in mathematics. While when you talk about electroweak theory or the quantum chromodynamics QCD, there you have the Lagrangian densities, and the Lagrangian density in electroweak theory indeed remains invariant under the gauged SU2 group of left-handed doublets, but it's also invariant under U1 group. So in electroweak theory, the group was SU2 left-handed cross U1 group. Yeah, Sajal, yes, on Tuesday we can have the class at 7:30 p.m. instead. If everyone is uh, willing, then at 7:30 p.m. on Tuesday we can have the class. Okay? So is it all right that at 7:30 p.m. on Tuesday we'll have one mathematical physics lecture? And I will send you, if my internet doesn't improve by then we will have to again use the same StreamYard for the lecture, because I find that the Microsoft Classroom slows down further. Yes, Rupesh, I will upload up to whatever I have done today. I'll upload in the Microsoft Classroom all the lecture notes. I'll do that. Yeah. Are there any more questions on any topic in mathematical physics? Need not be about today's lecture alone, but if there is any question, please go ahead. Sahil, the point is that if the internet improves, then we'll go back to Microsoft Classroom. There, of course, we have the voice chat option. But in the StreamYard, unfortunately, for such a large group of students, we don't have the direct voice chat option. You're welcome, Shubham. So if there are no more questions, I'll end the broadcast, and the same lecture you can find in the YouTube. This will be permanently, this particular lecture has been recorded permanently and it can be accessed in the YouTube. So if there are no more questions, I will end the broadcast. Okay, thank you everyone for joining me. So our next class is going to be on Tuesday at 7:30 p.m. See you then. I'll end the broadcast now.